Good afternoon, everyone, and welcome to the most recent 2DCC webinar. Today we have Dr. Zicheng Mao, who recently moved to Penn State from Tulane. He's in the Department of Physics, and he'll be talking about bulk single crystal growth today. Dr. Mao?
Okay, thank you for the introduction. It's my pleasure to have this opportunity to give this presentation. So today I'm going to talk about bulk single crystal growth of novel quantum materials. Here's the outline for my talk. First, I will give a brief introduction to fundamental concepts of crystallization, and then I introduce several crystal growth methods, including solution growth, chemical vapor transport, the Bridgman floating zone. And so these methods, these three, solution, chemical vapor transport, floating zone, are heavily used in my research. And Bridgman is used by 2DCC right now. And then I will talk about a strategy for crystal growth of materials without known phase diagram. So that's usually very challenging. So I'm going to talk about the strategy. At the end, I will make a brief introduction to my crystal growth effort of novel quantum materials. Okay, so single crystal refers to the material with constituent element arranged in periodical pattern along x, y, z direction, as shown in this diagram. This is one example. This is diamond, so meaning carbon atom arranged periodically along all three directions. And this is contrasted with polycrystalline material, the powder, so which contains a number of micrograins. Each grain is a single crystal, but a different grain oriented a different direction. So that type of material is called polycrystalline material. Single crystal can be grown from polycrystalline material either using a solution method or a melt growth method. So I will talk about that later. Single crystal exists in nature. It can be grown in the lab. Also, you can find them in nature. So here are some examples, like quartz, ruby, which is a luminous oxide doped by chromium, or blue sapphire. All these you can find in nature, which is also aluminum with different impurities. So these natural crystals, are good for making jewelry, and diamond is very expensive. You know that. So single crystals are also very important for industry. They have a wide range of applications in industry, including silicon chips, the laser, solar panel. The solar panel could use both polycrystalline silicon or single crystalline silicon. But the single crystal silicon panel has much higher efficiency than polycrystalline panel. So that's why single crystal silicon production is very important for industry. And also I want to point out single crystal samples are critically important for revealing underlying physics of quantum material. The research of quantum materials is at the forefront of condensed matter physics and the material science. So getting single crystal sample for the studies are critically important. Example of quantum materials include unconventional superconductors, strong core materials, and magnetic materials, low-dimensional materials, and topological, and many others. So many examples. So getting single crystal is really important for research. So the next I'm going to talk about the crystal growth method. So in general, crystal can be grown from a melt or solution or vapor phase or even solid phase. So in general, we divide growth technique into 4 different kinds as listed here. And we also can regroup them in a different way in terms of growth temperature. So high temperature growth, so you will usually use this method. So Caesar, Tarowski, Bridgman, floating zone, that's high temperature, usually above 1200 degrees C. Medium temperature method including flux, vapor transport, hydrothermal, electrochemical from melt, summation, and usually the growth temperature for this technique below 1200. A low temperature method usually is below 100. So in this presentation, I'm going to introduce these four methods: Flux, CVT, floating zone, and the Bridgman. So which are heavily used in my research and also in 2DCC. So first, I want to talk about a driving force for crystallization in solution growth. The solution growth is one of the major methods used in synthesizing quantum materials. So I will start with that. So in solution growth, of course, to build single crystal, you need to have crystallization, right? That means that the liquid phase need to nucleate and then gradually develop into single crystal. So usually it undergoes two stages in crystallization. So first stage is the formation of three-dimensional microscope nuclei. Of course, first of all, you need to prepare a solution. So to prepare a solution, you need to dissolve the compound in solvent, or also you can call it solution, right? So you need to find appropriate solvent to dissolve the desired compound, polycrystalline material, right? And then you want to, nucleation happens in the solution, right? So this can be done by several approaches, which I discuss in a few minutes. In the second stage, when nucleation occurs, they need to grow to large single crystal visible to your eyes. So two stages. Then the question is, how does crystal nucleation occur? How make it happen, and how they happen? We need to understand that, right? So what's the principle they follow for nucleation? So to understand that, we first need to understand these two concepts. So one is the solubility, as shown in this diagram. So solubility, when you dissolve a material in a solvent, they are dissolved. It is dissolved, and it has a certain concentration. Solute has a certain concentration, right? So this curve refers to the equilibrium solute concentration. So this curve is also called solubility curve. So this is at equilibrium. But you can add more solute to solution, right? So in this case, and then the concentration at finite temperature, the concentration would be higher than the equilibrium solute concentration. So, and then when this happens, we call the solution is saturated, right? When you continually add more solute, the concentration will further increase, right? And then we call supersaturated, right? So this curve is called supersolubility. So that refers to limiting value of solute concentration. So when you reach this concentration, then nucleation will happen instantaneously. So precipitate will start to take place from above this curve. So the crystallization requires a supersaturated solution. So in this region, the nucleation will never happen. In region below this curve, solid curve, you don't expect any nucleation. And then you may say we should go to this region. We can get nucleation very quickly. That's true. So if you if you reduce temperature from A quickly into this region, so you will reach the supersaturated region now. So in that case, solid will start to nucleate very quickly and very fast. But actually, that does not favor crystal growth. You have too many nucleations; they happen very fast, and also that process introduces a lot of defects. So crystal cannot be made large. You can get microcrystals in this region. So this is the region for crystal growth. That is called mid-stable nucleation zone. So here is not super saturated, but it is saturated. So in solution growth process, so what's really important to us is this mid-stable nucleation zone. And then, so then we wonder how we get to this mid-stable nucleation zone. There are three approaches. One approach is cooling the solution. Let's say we start from point A, and then we gradually decrease temperature. So when it passes point B, so the solution will saturate, not super saturated, right? So then it enters mid-stable zone, nucleation zone. So this is one approach. So you can move from undersaturated zone to mid-stable zone by cooling the solution. The other solution, the approach, is the solvent evaporation. So at the finite temperature, if you evaporate the solution, the solvent, the concentration will increase, right? If you start from here, and evaporate the solution, the concentration will increase, right? It will enter first mid-stable and then super saturated, right? So that's the second approach. Or you can do combination, cooling and the evaporation. So the crystallization speed actually is dependent on the supersaturation. So supersaturation means the difference of solute concentration. So if you start from A and then decrease temperature to this point, so to T1, from T1 to T2, so the concentration then will have difference, right, between C2 and C1. So crystallization speed actually is proportional to that supersaturation. So here M represents the number of nuclei formed per unit of solvent volume now. So from the above discussion, now we can see the driving force of crystallization is supersaturation. That's the key word, right? So we need to have supersaturation to have nucleation and crystal growth. But you don't want to get into this region, supersaturated, unstable region. But you should get into the mid-stable saturated region. And the supersaturation can be measured by this concentration difference, as I just explained, when T is decreased. And then you wonder why this. So this is an experimental observation. So what's the physics behind this observation? So here is the physics behind. So actually, this nucleation and the growth of crystal, is governed by the change of Gibbs free energy. So here delta G represents the change of the Gibbs energy before nucleation, before a reaction, and this is the Gibbs energy of the final product. That means with the nucleation happening, the total free energy of the system will decreases. So in solution growth, the decrease of the free energy is proportional to supersaturation, so which is the difference of solute concentration. In melt growth, the principle is different. So melt growth, we don't use solution, right? You just melt the source material, which could be either polycrystalline material or element, right? So you just melt. You don't use any solution. So in that case, the decrease of Gibbs energy will be proportional to delta T. Delta T is temperature difference between the temperature of melt and the melting temperature of the crystal. Right? So the principle between these two growth methods are different. So next I want to talk about the nucleation process. So nucleation can take place in two different ways. So one is homogeneous nucleation. The other is heterogeneous nucleation. So now let me tell you what they are. What is the homogeneous nucleation? So homogeneous nucleation usually takes place spontaneously, randomly, and it requires supercooling of the solution, or you could say medium. Right? So if the solution has no impurity at all, so solution is very pure, right? And then the system will undergo a supercooling now. So let me explain what it means, supercooling now. So for a given solution, and then we decrease the temperature now. And then if the solution is very pure and in large container, and even in the metastable nucleation zone, it doesn't nucleate. So it's going to continue remain in a solution, pure solution, without any nucleation, down to point C. So beyond C, as I said, nucleation will happen spontaneously, right? So this process from B to C is supercooling now, right? For pure solution, that could happen now, right? In that case, it will be very difficult to get larger single crystal, right? Because nucleation will only happen in this region, right? In this region, we were not able to get larger single crystal, right? So here, I want to give you one example, supercooling. Supercooling of pure water. So now let's consider pure water. And then we reduce temperature. So we try to get the ice crystal, right? So in general, for tap water, if you reduce temperature, you will get ice at 0 degree C, right? But however, if it's pure water without any impurity, you cannot get ice at 0 degree C. Instead, you will get ice crystal when temperature reduced down to negative 48 C. The reason for that is the presence of supercooling. Right? So it remains liquid water down to this temperature. Right? And then when you further decrease temperature, it starts to nucleate, forming ice crystal. Right, and then you can further decrease temperature, and then when the ice ice crystal forms, and then temperature will go back to 0 degrees C. Of course, if you further decrease temperature, the temperature of ice can also further decrease. So that's the homogeneous nucleation process. So the other nucleation process is the heterogeneous nucleation. And this happens when the solution have impurity, like dust, or also the phase boundary, or even a surface of container can serve as the nucleation sites. So when you have nucleation can happen much easily, right? Of course, when you do solution growth, the solution has to be put into a container. It always has, the boundary. Yeah, in some case, a boundary could serve as a nucleation site. But if you have impurity, they can become preferential nucleation site. So when you have those, when you reduce the temperature and enter the metastable saturation zone, so you have some nucleation around the impurities, and then when you further decrease temperature, and then those nucleated particle will continue to grow and they become larger single crystals. Right? So that's the two nucleation process. So in reality, this nucleation process, heterogeneous, takes much more often than heterogeneous. Here's one example of heterogeneous nucleation. So this soda water. Soda water is carbonated water, right? To facilitate nucleation, you just dip your finger into the soda water, you will find a lot of carbon dioxide molecular or nucleate on your finger, right? So that's what it means, like heterogeneous nucleation. So here, when finger is dipped into the water, you have interface between water and the surface of your finger, right? That serves as the nucleation site, so that the carbon dioxide molecule can nucleate it. Okay, so next concept I want to talk about is nucleation barrier. So when you want to grow crystal, the nucleated particle have to overcome the nucleation barrier. So now we may use this curve to explain what it means, nucleation barrier. It's basically the change of Gibbs energy, the difference of Gibbs energy between Gibbs energy, interfacial Gibbs energy, and the volume free energy. Meaning, the free energy of nucleated material, the nucleated solid phase energy. So because when nucleus forms, you have a surface, right? So you have an interface between the particle and the solution, right? So that bringing interfacial energy, right? Increase energy. When nucleation happens, also this process also reduces energy in the bulk, right? So they compete, right? So if you add these two curves together, so then it becomes this green curve, right? So this delta G star is called nucleation barrier. So when these two energy compete, if this is much greater than this, and then you will be in this green region, right? So in the green region, the small particle can form, right? When they compete, can form, but they dissolve. They are dissolved back to liquid very quickly. So you cannot, get the stable a particle in the green zone. So thermodynamically, it's unstable in this zone. So in general, in this zone, homogeneous nucleation happens in this zone. And then when you further decrease temperature, in some case, so you can enter. In some other case, you cannot enter. In some case, you can enter the yellow region. So in the yellow region, the particle already overcome this barrier, delta G. So when the particle overcome that, then they can further grow and can further grow. And if you further decrease the temperature, they can enter the red zone. The red zone, this energy, overcome that interfacial energy. So that favor further growth of the particle. So then at the end, you can get the larger single crystal. So some case you are able to get larger single crystal at the end of the growth. That means you overcome the barrier, the nucleation barrier. You are here. But in other case, you cannot get single crystal, meaning you did not pass through that barrier. Important for crystal growth, you have to overcome that. But then you wonder, how can I overcome that? How I can pass that barrier? So this depends on what solvent you use in solution growth. So selecting appropriate solvent is critical for solution growth. If solvent is not the right solvent, that could be high. That will be difficult to grow crystal. Right. So the finding appropriate solvent, or also called flux, it's in some case, especially for growth of new material, it's difficult. And then, so next I want to talk about the criteria for selecting appropriate the solvent, or called flux. So this is general, just general criteria. So first, the flux should ensure sufficient solubility of the compound, right? When you select a solvent, you need to ensure that your material, polycrystalline material or element, can be dissolved in the selected solvent, right? If it cannot be dissolved, it will not be able to grow crystal, right? That's straightforward, right? And the second, the solubility should show sufficient change with temperature, right? So when we do cooling, slow cooling to the crystal, you want the change of the concentration is large, right? So you say if you cooling from A to E, so you want a large change of concentration between E and F, right? But if this curve has small slope, that change will be small. So as I just said, the growth speed is proportional to this difference of concentration, right? So the large slope of this curve is important, right? So meaning it should have a strong temperature dependence. And third, the flux material should have a lower melting point. If it has a very high melting point above 1200 degrees C, lower temperature growth, you cannot form liquid, right? Certainly cannot be used as solution, right, to grow crystal. So usually we choose a material which has a melting point below 1000, typical. Of course, the material needs to have a low vapor pressure. If it has high vapor pressure, when you do growth at high temperature, the solution just keep vaporizing, right? If your material is sealed in quartz tube, the high pressure will break your quartz tube, right? So you need to ensure your vapor pressure is lower. And also lower viscosity. The solution, if it has a high viscosity, that disfavors the formation of high quality crystal, because high viscosity could cause roughness between the surface, interface between the liquid and the nuclear particle, so that the interface becomes very rough, and then that will produce a lot of defects, and also even preventing formation, further growth of crystal. Of course, you want it to be low toxicity, and also it should not corrode the crucible and the furnace. So you have to consider that as well. And the last, the solvent flux, and needs to be easily separated from crystal, right? In general, we have several methods to separate the flux from crystal at end of growth, depending on what solvent you use. So here I list some commonly used flux for high temperature solution growth. So this includes the salts. All salts have many salts have a lower melting point shown here, or below 900. Some oxides also can be used as flux, such as borate and bismuth oxide. They also have a lower melting point. Or hydro oxides, or even low melting point metals such as tin, gallium, antimony, bismuth. So if a salt is used as a flux, it's easy to separate, right, from after growth. You just put your product into water, right? Salt could be dissolved in water. The crystal will not, right? So you can take the crystal out from the water. That's easy. But if the metal use the flux, it cannot be dissolved in water, right? And then you have to use a centrifuge to separate the excessive flux metal. The centrifuge, that means when we do it, we need to put the sealed quartz into a furnace to heat it to high temperature. But of course, you need to make sure the temperature is not higher than the melting point of the crystal, right? Otherwise, your crystal will melt it, right? So you need to find a temperature which is below the melting point of the crystal. So heat it for a few minutes, and then you quickly take it out from the furnace and put it in the centrifuge. Centrifuge for 1 minute, 2 minutes, and then the excessive flux will be separate from the crystal, the implicated crystal. In some case, we also use some acid or special chemical solution to dissolve the flux. Also, I want to briefly mention the self flux. So self flux, meaning in this growth, you don't have to add any solution solvent. If the starting material including element which has a low melting point, so that element itself can serve as a flux. At the same time, it also reacts with other elements you add, right? So it's like the melt growth, right? Melt growth. So in that case, it's easy, but we cannot be always lucky. Some material can be grown that way. You don't have to find any solvent, right? It just you mix the chemicals, right? Of course, falling, the more ratio, right? Depending on what material you grow, and then you heat it up to high temperature and melt all elements, and then at the end they will form crystal. So that's a straightforward and easy. And also, I want to make some comments on choice of a crucible. So first, crucible needs to have a high melting point, right? Otherwise, when you heat it to high temperature, it will be melted, right? So typically, we use these type of crucibles, aluminum crucible, zirconium oxide, or platinum, tantalum, and iodine. All these have very high temperature. We often use this, and these two very expensive. So I never use this because it's too expensive. You know how expensive it is, right? But in future, we are going to use this. 2DCC has purchased equipment which allow us to see a material in tantalum tube, right? So we will be able to use that in future. Okay. So next, I want to briefly talk about the process of the crystal growth techniques. So depending the method of achieving supersaturation in the solution, the technique of crystal growth from high temperature solution could be grouped 3 types, as listed here. So as I said earlier, supersaturation can be achieved by either cooling, so that method is called slow cooling method, or could be achieved by evaporation of solvent, so that is the solvent evaporation method, or could be achieved through setting up a temperature gradient in solution. So here I just want to make a brief comment on slow cooling now. So this is show you how we group crystals through cooling. So if you know the melting point of the desired compound, then it's straightforward. It's a lot easier. So you first either use element or use polycrystalline material as a source material. So if polycrystalline material is made and you know its melting point, you just increase temperature above 50 Kelvin above its melting point, right? So by the melting point, so the polycrystalline material will melt, right? But the temperature need to be higher to get the more homogeneous of liquid. So 50 Kelvin usually is high enough for getting homogeneous solution, and then you do very slow cooling. The cooling rate usually is between 1 and 3 degrees C per hour. That's what we usually use. So the slow cooling, ensure we will enter the metastable nucleation zone, right? If you do very quick cooling, like 50 degrees C per hour or 100 degrees, you will jump into this rate, right? And then in that case, you just have homogeneous nucleation. For that, you cannot get lost in the crystal. Okay. For this method is useful for growing material which is stable only in very narrow temperature range. If this is the case, you cannot use this method of slow cooling down. So you have to evaporate solvent, right, to increase the concentration to reach supersaturation. But however, the control of the evaporation of solvent is not that easy. So I never use that method. But this can be done. Next, I want to very briefly introduce chemical vapor transport method. So here, I just assume we make a binary compound using chemical vapor transport. So to do that, if it's an intermetallic compound, we have to seal the material in a quartz tube. So we put the source material. They could be element or could be a polycrystalline material. We'll put it in a hot zone of a double zone furnace. So it has a temperature gradient. There's a hot zone, that's cold zone, right? And also you need to add transport agent. So here, which is represented by air, that's transport agent. So when A or B, both needs to be, has a high vapor pressure. When they are vaporized, one of them could react with transport agent, forming a new molecule, A or B, right? And then they are transported to a lower end. At the lower end, so this molecule will react with the other element, forming the desired compound at the cold end, as shown in this diagram. So the principle of this method is pretty simple. So next, I want to talk about the Bridgman method, which is being used by 2DCC. I have never used it, but I will use it in future. So this slide summarizes the growth of crystal using Bridgman method. So this method is, as I said, it's being used by 2DCC. So Sam Lee is an expert of crystals using this method. So now let me very briefly introduce the principle of this growth method. So it's melt. So first of all, this method is melt growth. It's not growth from solution. It's melt growth. So this diagram shows you the process. So for this curve shows the temperature profile of the furnace. So furnace have a 3 temperature zone that could produce this temperature profile. So first step, we seal the source material in quartz tube. And then we increase temperature to allow reaction to happen, and forming temperature needs to be higher to get a liquid phase, a homogeneous liquid phase. And then we translate this quartz tube to cold zone, as shown here. So when liquid cools down, we will crystallize. At the end, and then we need to anneal so when solidification finishes, so then we need to anneal the product at a certain temperature, which depends on the material you grow. So this method is very effective in growing most topological insulators, as shown here. So this is a crystal, beautiful crystal grown by Dr. Shan Li, and this crystal are grown by Dr. Schneider's group. So that the quality of these crystals are pretty high, as shown by in this X-ray diffraction. So finally, I want to talk about the floating zone growth technique. So this technique, was designed probably in 1950 for silicon crystal growth. So the other major method for silicon growth is the Cauchy method, right? But however, this method for growth of silicon has an advantage. So that advantage is the impurity concentration in silicon crystal could be 2 to 3 orders of magnitude smaller than the CZ, the growth crystal grown by this method. So that's the. So in this method, the heating source is the inductor, which is just a plate-like single tone coil, and then you apply high frequency signal and generate heat in the zoom. So that can melt the material. So crystal could be made very big and very pure. And then in 1960s, the optics Fourier zone was developed by these two people. So in this type of Fourier zone, the heat source is not inductor. It's a lamp. Could be halogen lamp or could be xenon lamp. That is much more powerful. Or could be laser. So my Fourier zone furnace use halogen lamp. So here's schematic of the Fourier zone. So the lamps are mounted on their focusing point, and this point is their shared focusing point. So as you can tell, the light reflected from internal surface can refocus at this point, right? So that temperature could reach, for my Fourier zone furnace, could reach about around 2,000 degrees C. In some case, if this is used, can go up to like 3,000 degrees C, which I don't have. And then, to make crystal first, the first step, you need to make a rod, a material rod, feed rod first, right? So you use polycrystalline material, powder, to make a rod. So because of limited time, I will not introduce the details of how of making a rod. And also you need to make a seed rod using same material. The seed rod could be a polycrystalline rod or could be single crystal. But using single crystal, it has advantages. It could, quickly make nucleation happens, and the crystal growth can take place very quickly. And also, you can control the orientation of the crystal. So the advantage of this method, does not use a crucible, so that you will not get contamination from crucible. So that's why the crystal grown by Fourier method could be very pure, and the crystal could be very large, and large crystal very, very useful for neutron scattering, for physics study, and also of course for the industry applications. And also, so in this technique, the thermal gradient on the crystallization front is very high. So here is the crystallization front. The thermal gradient is very high. That decreases the danger of supercooling. So we don't want supercooling, as I just explained. So that enables the faster growth. And also, this type of furnace has a CCD camera behind the furnace, so which allow you to observe the crystal growth and also remote control. So this type of the growth method, has gained popularity for fast growth of oxide, which are difficult to be grown using other methods in past decades. So the oxide growth are most of based on this method, optical Fourier zone growth. So I tell you a little bit about the growth process. So at the when you increase the temperature of the melting zone, then you get some liquid right from the feed rod, bottom feed rod, and then you connect it with the seed rod, right? So at the beginning, no nucleation happens. As time goes on, you get some micro grains, right? And then it will continue to grow the small crystals, right? But we don't want to get crystal with many domains. So so you have to adjust the growth conditions. Many parameters could be adjusted. So when it's ideal, so one domain will dominate, right? So the growth speed of that domain it should be higher than any other domains. So eventually, will continue. You will get larger single crystal. So the quality of the grown crystal depending on the growth stability. So the key point for floating on crystal growth is to keep the stable growth. So stable growth depending on many factors as listed here, depending on the shape of the starting rock. Okay, 10 minutes. Okay, I'll finish in 10 minutes. The rod needs to be straight and uniform. So sometimes it's very difficult to make such a straight and uniform rod. And you have to align these two rods, in excellent shape, where they have to be aligned, right? Their axis has to be aligned along central axis. If it's misaligned, that could cause problem, right? You will see this when they are connected. You will see this. When this happens, you cannot get a good crystal. And the viscosity, viscosity depending on the heating power. Right? Heating power can be controlled by the voltage. If viscosity is lower, this will happen. The melting zone will become very thin, right? Then it will could become separated between feed rod and the seed rod. So the viscosity needs to be moderate. It cannot be very high. If it's very high, and you can, as I said, it will produce a lot of defects. And the ideal shape is like this. It's like T shape shown here. That's ideal shape for crystals. And sometimes if the material has a high vapor pressure, you need to apply pressure to suppress the evaporation. Okay, so those factors could be optimized to maintain the stable growth. So this is my floating zone furnace moved from 2 lane. So this one has 2 mirrors. Maximum temperature is 2150 degrees C. So what is unique with this furnace is it has equipped with a cold trap. You cannot see it. It's here, the cooling water running into this force tube, and so that could attract, vaporize the material. Otherwise, the quartz tube can get contaminated very quickly. And so this is a custom design. So this is used for oxide growth. So it will be installed in my lab here. And I also originally purchased the quantum design floating zone furnace. This is new. It's already delivered. It will be installed soon. It also has 2 mirrors, cold trap, but temperature is not that high. This is less than 2000. So this will be used for growing intermediate compounds. Okay, so this is my new lab, synthesis lab, still under renovation, right? So, but the floating zone will not be put into this lab. There will be in a separate lab. So this lab will be equipped with many furnaces, including multiple zoom furnace, crucible furnace, Marfo furnace, and also plan to buy a arc melting furnace for this CZ growth. And the 2DCC also, will be put here, and I will also get the tantalum tube sealer. Okay.
Dr. Mel, the person's leaving the webinar and they have a question.
Okay.
The question was, can you name some methods on how to cool solutions slowly? I think they were curious about that.
So the cooling rate can be controlled, right? So it's in a furnace, which has the capability of programming, and then you can control the cooling rate, right? Okay. Yeah, that can be done through the program.
Okay, does it matter per machine? So, for example, if you have a floating zone versus a Bridgman, are there different techniques?
Okay, for solution growth,
yes,
that could be done by programming. For floating zone growth, the growth speed is controllable. So you can the range from 0.1 millimeter per hour up to 60 millimeter per hour. So you can tune growth speed. Yeah, when the growth speed is slow, you have 2 consequences. One is you have the vaporization is high. But the cooling rate is still there. Cooling rate is still the same. The cooling rate is lower. It's lower. So it can be controlled by the growth speed. Yeah. Okay. If you want to finish with 5 minutes, and I will skip this slide. So at the end, so I will skip these slides. So this slide basically I just want to tell you now. If you want to grow a new material, new complex compound with unknown phase diagram, how we do that? What method we should use? So this diagram show you, what strategy you need to follow to identify appropriate growth method So I'm not going to discuss it because it takes time. So anyway, you can look at my slides. It's explained here. So this is an example. So in the last few minutes, I want to make a very brief introduction to my research. So my research interest is to discover and understand new quantum materials through synthesis and the characterization. So this summarizes what I have been doing and what I will do at Penn State. So basically, crystal growth, material characterization, property characterization, structural characterization, and the material physics. We also study material physics, including superconductivity, magnetism, quantum transport, and topological properties. So we have been using solution method, kinetic vapor transport, and the floating zone to grow crystals of many different kinds of quantum materials. So this including superconductors, topological materials, Dirac walls, semimetals, and low-dimensional materials. In recent few years, we have made a lot of effort in growing this type of material, layered magnetic materials with randomized gap. So all these I'm showing magnetic order or either antiferromagnetic, ferromagnetic order, and then they have randomized gap so that we can exfoliate to achieve 2D materials. So we have made a lot of new 2D materials as shown here. So we have demonstrated these are old materials and not studied before, synthesized before, but not studied. So we made single crystal of these materials using the method I just introduced. So we have shown all these 2D materials show very interesting properties. So I'm not going to tell you the details of the method. And also I want to tell you, oxide, should be grown using floating zone. So we have been growing a lot of oxides, mostly leucine and magnetite. So I have done a lot of study on these materials. Actually, that's my background. These are strongly correlated materials. I have done a lot of work on that. And so finally, I also want to tell you, my research has been focused on these fourth direction, superconductors, exotic phenomena of correlated materials, topological, and the 2D materials. So here are some representative publications. So at the end, I want to acknowledge my collaborators. So these are my former group members. They have already graduated, and Yang Lin Zhu, not graduate, has already here. Will be graduating this year. So now I'm building up my new groups at Penn State. So Xiang also is partially working with me, and also I recruited several new students. And the work I have been doing, supported by NSF DOE. Recently, I got some support from 2DCC-MIP, and also I have, given we have a capability of growing a wide range of quantum material, we have opportunity to collaborate with many other research groups, as shown in this map, and list the names, and also acknowledge opportunity collaborating with them. Okay, that's the end of my presentation. Thank you very much.
We have two current questions online. Number one is, why is a T-shape ideal for the floating zone melt?
Okay, so if it is I-shape, very thin, I-shape means a very thin melting zone, right? So when that happens, it means the viscosity is very low, right? Viscosity, so the liquid will cools down very quickly, right? When this happens, it cannot, it will nucleate, but cannot continue to grow, right? So this is related to viscosity. The T-shape has appropriate viscosity. So you want to hold the liquid phase in the hot zone for a while, and then gradually cool it down, right? If you cool down very quickly, just drop. If you drop off, it will not crystallize, right? So that's why T-shape is important.
And the second one online is, how can we get rid of forming multi-component twins, especially in solvent evaporation method at low temperature?
How we get rid of what?
How we get rid of forming multi-component twins?
Multi-component twins in solution growth.
In solvent evaporation.
Yes, solvent. It's unavoidable that this happens quite often. as long as crystal size is large, you can always separate them, so they could be twinned. The different crystal oriented along different direction, but they are combined, right? And then you can cut it, right? You just cut the part, right? But growth itself, it's you cannot control it.
Questions here on site?
So the slow cooling method, you said there would be less homogeneous nucleation when you cool the solution really slowly, right?
Yes,
So would it,
slow cooling is
Slow
important.
cooling.
Fast cooling,
More
you
homogeneous.
will go to the unstable
right,
supersaturation.
So would it also be applicable for a solid substance, like if you have an amorphous substance and you heat it to a high temperature and then cool it really slow? Would that
Yes,
be-
that also applicable. So if you have polycrystalline material with some micrograins, stuff, and then you have to cool down very slowly for a long time, much longer time than the solution grows. And then if you're lucky, you are also with the good zinc crystal. Yeah, we did that before. Yeah, slow cooling
What sort of time scale does it take?
a couple of weeks. Yes. Yeah, we had one growth. It takes like 1 month nearly.
So you mentioned a lot of flux mediums. How about the use of ionic liquids for low temperature solution growth?
Ionic liquid, like the sodium chloride, when you heat it to temperature, this ionic liquid.
Yeah,
right?
well, more like organic ionic.
Yeah, ionic organic can also be used as well.
Is there any difference between because you would use those in low temperature, right?
Right. Yeah, so the organic, the solution usually used for low temperature growth. Yeah, I'm not sure if they can be used for high temperature solution growth, but from literature, what I learned is that organic solution usually used for growing crystal at low temperature. Mostly it's organic crystal, not inorganic crystal.
But organic ionic liquids can dissolve in organic molecules, like metals. So can you use that for low temperature crystal growth?
Yeah, I think they can be used for low temperature growth, but I'm not sure if they could be used for high temperature growth. So from literature, I haven't seen anybody use organic solution, ionic solution to grow material which has a high melting point. Yeah, so but this it will be interesting to explore it. It might be useful.
When a synthesis takes a couple of weeks, that's kind of a long time to wait around.
Yes.
I wonder, when it takes that long for just a single experiment, are you ever sure that you've optimized your synthesis, or do you just get to a point and say, I guess that's good enough?
Oh, yeah, that's a good question. If it is a solution growth, if do single batch growth, you have to wait a couple of weeks, right, to see what happens, and then you choose. And so that's not efficient, right? Not and what we do, we make multiple batch, 5, 6 batch, or even 10 batch, same time, with different. We'll put them in different furnace, right, and grow them with different temperature, different conditions, right, and then we compare them, and then we can find what conditions are optimal. So that will be much more efficient. But for photon growth, it's difficult. You cannot, do multiple growths at the same time, right? It's only, one growth at a time, right? Usually one growth takes 1 week. You need a couple of days to make a rod, and then growth may take, even fast growth takes 1 day, right? Slow growth, if you use the growth speed of like a 1 millimeter per hour or even below 1 millimeter per hour, it takes a week, right? And but of course you cannot stay there for the whole week, but you still need to look at it time to time, right? So in that case, you have to use a remote control, right? Even at night, you want to take a look at your growth, right?
Let's thank Dr. Mao one more time.